And now we continue. Actually, we have the fortune to, at least she works in Bavaria now. I have like home feelings, you know. It's a great pleasure now to introduce to you a real expert on dots. And I think you can already see that she's really a dot expert. There are only dots in and on her and behind her. And how that comes tells you Paula Weber from Würzburg.
Yeah, hello, thank you for the nice introduction. And tonight I want to tell you about dots and stripes. And first I would like to, this is different. Trained with a different one. Okay, thank you. So still these nice dots, perfect. And but now we come to stripes, because in my childhood, my mother was giving me clothes, and she really liked to put me into stripes. So like t-shirts, sweatshirt, trousers, socks, everything what you can imagine of. So as a kind of a rebellion, in my youth, you can see it on a nice Czech drink in my hand. I was so much interested into dots. It felt like a liberation. And I really, like you can see, I'm into dots, like dress and the sweatshirt. It's perfect. And so, as I'm so much interested into dots, also into my scientific career, I came into dots. So I am from Düsseldorf, and I looked onto microscale on dots in printer toners. And then for my master's thesis, I took a look on nano dots in bacteria. Very interesting. You can hear more, I think, tomorrow. And then I came to Würzburg, and I wanted to take the ultimate challenge. I have here like a thin surface, metallic surface, and then with this I'm shooting atoms, like really, really small dots. I'm shooting, yeah, that's with this. Don't get interrupted that it's like a water canoe. No, it's like a dot evaporator. And then I take it to my microscope. And, oh no. These are not dots. No, this looks like I thought I would not see them again. Stripes. So why do we see stripes on thin magnetic surfaces? It seems to be like a magnetic atomic question, so let's dive into the atomic perspective of magnets. So first, in the middle, we have the nucleus, and around, like in an orbit, an electron goes, and this electron has a spin, like a self-around torque. We can simplify it. And so this would be like hydrogen. It's now also very important for energy. We can make this atom a little bit bigger. We can also take another electron. And so now it could be helium, but this has also a spin. So, oh no, in the other direction, because I'm Paula, I can't violate the Pauli principle. Sorry. So we have these two electrons with spins, but now we are interested in magnetic atoms. Or like, for example, an iron atom. On the left side, you see something like an iron material, gray, a little bit clumpy. in the middle, like the atomic model of it. For simplification, it could be also lithium, but I just want to show you that we are now interested that we have one spin more in the outer shell, and this makes the spin direction of the complete atom. Now we have one defined spin direction. And when we now go to magnetic domains, for example, of iron, then they are very parallel to each other. And we call it like iron magnetic, or for the Latins under you, like ferrum. And here you can see the iron again. But what we also find in nature is anti-iron magnetic, so anti-parallel spin directions. And so antiferromagnetic. And here you have an example of an antiferromagnetic material. It's manganese. But now, we see that we have the two gray clumpy materials. Can't see anything. How to distinguish that we find parallel or anti-parallel spins? When we physicists want to take a look about something very small, we take like a big microscope, like you heard already from big things, like you heard already from Judita. And here it's a scanning tunneling microscope. You can see it in the size comparison. And this microscope can distinguish spin directions. This is, we have a small tip. And on the tip, we put a definite spin in one direction. Then we scan over a surface, and the surface has spins, for example here, antiferromagnetic. And when we have like a spin of the surface in the same direction, then we have a bright outcome signal, and in the other direction, so antiparallel, we have dark outcome. And so this looks very nice, like a checkerboard. Let's test it on our scribes. Sorry, I still hate to see this. It doesn't look really like that, I would say. It looks more like 3 different brightness levels. So like bright, middle, and dark. But what does the middle brightness level mean? It looks like an antiferromagnetic pattern, what you also can find in nature. But the middle one looks like it can't decide solid between its neighbors. Shall it go like in the one direction, but then the other spin would be angry, and the same would be for the other neighbor. How it can be happy? And let's take a further look. It seems to be really frustrated. And it's not like an emotion, it's really a scientific term in our community. So, what will it do? Will it go in this direction or in this direction? It will bend to the side, so like this. So it will, or it can also flip to the other side. And it can also like 45 degrees, and then go more near to the other spins, and then or the other direction. And there are so many possibilities. If there wouldn't be a Schreck now, I just would like to go back to Würzburg and complete my go further on my measurements. And with this, I would like to tell you the moral of the story. I would say my mother is right. Scribes are cool. Don't worry.
Paula Weber.
Thank you.